This is the most complex and sophisticated machine ever made. In 6 minutes, it will be traveling at 17,500 miles an hour. In 8 minutes, the humans inside will no longer feel the pull of the Earth's gravity.
So the space shuttle launch used to take 8 minutes. So within 8 minutes, they had to travel 180 miles while reaching their final speed of 17,500 miles per hour. All right, so you got 8 minutes to travel 180 miles while reaching the final speed of 17,500 miles per hour. The problem with that was within that 8-minute time span, not a single person was in charge of the shuttle. No one is piloting the shuttle within that 8 minutes. So under the circumstances, for things to go right, they had to make motion predictable. So the question is, how did they make motion predictable? How do you make motion predictable?
There is no danger,
Predictable motion means a couple of things.
An uninhabited part of the Australian outback. Scientists say.
So when motion is predictable, in this case, the satellite is coming down, you know when it's going to land. So when is the time is determined, how fast and where. All right, so you will know where it's going to land, how fast it's going to land, and then when it's going to land. All right, so the three things that become predictable. So this is known as predictable motion. If you know when, it's predictable. If you know how fast, it's predictable. And if you know exactly where, it's also predictable. So the motion becomes predictable. So that's going to allow you to be able to do forecasting. So this guy is at the landing mark. So he's obviously ready for impact.
Do you, Yahoo?
Not only is he ready for impact, but also notice that his dog is. All right, let's talk about impact just briefly because it's the past lecture, right? What makes impact survivable? You're looking at it. The pillows in this case is going to help, right? Why? From your perspective, oh, because they're cushioned. No, from my perspective, because they increase the impact time. Got it? So what happens when the impact time goes up? The acceleration goes down. Acceleration is what kills you, what maims you, what breaks your bones. All right, so during impact, what's happening is for it to be survivable, you have to increase the impact time. That's all you have to do. All right, so some basic facts. This measured distance over measured time is going to give you an average speed. If you include direction, it turns into velocity. How fast the velocity changes in time is your acceleration. Meaning how fast you speed up, slow down, or change direction is your acceleration, right? Speeding up is acceleration. Changing direction is acceleration. It's changing speed as well as the change in direction is acceleration. Now the acceleration is about to change because you're about to impact. So when the acceleration changes in time, we call that jerk, or the average jerk in this case. So what's happening is your acceleration is going to be changing within this time period. So you're looking at a graph of a acceleration versus time graph of a car collision within 10th of a second. So the acceleration keeps varying, keeps going up and down. That's what it means. Acceleration keeps going up and down. Peaks at 150 Gs. So the question is this survivable? If you're looking at the peak acceleration, you may say, no, it's not because you can survive only up to 140 Gs. That's not the way to look at it, though. What you need to do is the peak acceleration is not what determines what's survivable or not. It's not the minimum acceleration either. It's the average acceleration. So the average acceleration is about 20 to 25 Gs. So 20 to 25 Gs up to a 10th of a second is survivable, a fraction of a second survivable. So notice that the acceleration is changing here. So it's a variable acceleration, which is otherwise known as jerk. So in jerking motion, if there's jerking motion, we use the average acceleration in order to estimate the acceleration. So changing acceleration in time is called jerk. If there's jerk, we use the average acceleration to get an estimate for the acceleration. Prime example is the car collisions. So how does one make motion predictable? When you have a variable acceleration, when the acceleration is changing in time, that motion is jerking motion is unpredictable motion. You want to make motion predictable, you have to eliminate jerk. Make sure that the acceleration is not changing, which means that if you're speeding up, make sure that you're speeding up at a constant rate, slowing down at a constant rate, or changing direction at a constant rate. So when the acceleration is constant, the motion becomes predictable. So when you fix the acceleration to a constant value, when you make sure that there's no variation in acceleration, the motion becomes predictable. All right, so three things about the motion is going to become predictable. Obviously, the time is going to be predictable. So for a given time and given acceleration, the location will become predictable. That's what the first formula says. If you know the time, you know exactly how fast it's going to move at that time. So that's the second formula. If you know the time And if you know the location, you will know how fast it's going to move at that location. So that's the third formula. So the first formula is going to locate the object for you at that time. So you know the time, you know the location. Second formula is going to tell you how fast it's moving at that time. So you know the time, you know the speed at that time. And then the third formula is going to tell you how fast it's moving at that location. So you know the location, you know the speed at that location. All right, so that's it. So the motion becomes predictable when the acceleration is fixed at constant value. All right, so you know the time, you know the location at that time. You know the time, you know how fast it's moving at that time. You know the location, you know how fast it's moving at that location. So 3 formulas and 2 things will become predictable. For a given time, location is predictable. Speed at that time is predictable, and the speed at that location is predictable. All right, so we looked at the lecture, we looked at Apollo 13. All right, we focus on a few scenes from the movie. Apollo 13 is the mission to the moon, obviously, on the way to the moon. Oxygen tank exploded. So the question is, how do you bring it back? All right, so there are 2 options explored in reality. Number 1, stop and come back. So how do you stop in space? Not that easy, you don't have friction. So you have to use the rocket fuel and fire the rocket fuel in the opposite direction of motion until you come to a full stop. And then you need to accelerate and come back on. So that was one option. So they decided not to exercise it because they didn't think that was the best option. Instead, they decided that they were going to do a slingshot around the moon. So that's the option that they decided to explore. So they would go near the moon. And then as they started to come closer to the moon, they would slow down. And then in order to escape the moon's gravity, they would speed up. So they would fire the rockets in the opposite direction of motion up to, I don't know, 6-7 seconds to bring the speed down. And then in order to escape gravity, they would just speed up. All right, so they figured out the free return trajectory first. And then they decided to place the astronauts on this free return trajectory. So that's how they decided to actually do this. All right, I gotta change the mouse. Okay, so they were slowing down and speeding up because they wanted to remain in a predetermined trajectory. They had to make motion predictable. So that's the way they traveled and they came back. So it worked out. So they make the motion 100% predictable. All right, so moving forward. So what happens within that 8-minute span? All right, so I turned this into a problem. The only thing you guys need to know is the end results. Okay, so you guys are taking conceptual physics. There's a little bit of math involved at this point. The math is just follow it. Just have enough understanding of follow the math. So miles per hour to meters per second. So I'm doing a conversion just to make sure that everything is expressed in terms of metric units. Miles to meters. We've got 3 formulas available for uniform motion, predictable motion. All right, so the question is, we're trying to figure out the acceleration. Based on what's given, we picked the best formula, so that's the last one. And then solve for A, so you know the initial speed is 0. Plug the numbers in. And we end up getting a number which is 105 something, and then that's about 10.5 Gs. All right, so if you fix the acceleration to 10.5 Gs, motion is predictable all the way up to 180 miles. And then your final speed is going to be 17,500 miles per hour. And then we'll figure out the time it takes for us to actually travel this distance while reaching the final speed of 17,500 miles per hour at this acceleration. And when we do that, we realize that we end up getting the time in terms of seconds. So it's going to be 1 minute and 14 seconds. All right, so if you fix the acceleration to a constant value, it's going to take 1 minute and 14 seconds to actually get up to the orbit while reaching the orbital speed of 17,500 miles per hour. Except we take 8 minutes. So one question is why? This is because of the acceleration. 10.5 Gs up to a few minutes is survivable. So that's not the problem. But 10.5 Gs at takeoff is going to destroy the shuttle. All right, so they wouldn't, because the air pressures, it would be so large that the shuttle would just shake itself to pieces. So they're not going to do it. During takeoff, it's about 3 to 4 Gs. So they end up using constant acceleration at variable stages. So that's the reason why they have variable rocket boosters, multiple stage rocket boosters. So each stage is going to have its own acceleration. So they take their sweet time So instead of getting things done within 1 minute and 14 seconds, they get things done within actually 6 minutes. By the time they're in orbit, it takes about 8 minutes so that the shuttle is not breaking apart. All right, so that's what they do. So NASA makes motion predictable by fixing the acceleration to a constant value. So speaking of fixing the acceleration to a constant value, a couple of things to discuss. All right, so let's get back. This acceleration, which is changing there, is the measured acceleration is changing within this time period. So the acceleration goes from this value to that value. At this moment, your acceleration is at this rate. At a later moment, your acceleration is at a different rate. All right, so these are known as instantaneous accelerations. So what's changing here is the instantaneous acceleration is changing in time. That's what it means. All right, so in these formulas, when we start off, measured velocity is changing in time. So instantaneous velocity is changing in time. So that's going to give you average acceleration. Changing instantaneous acceleration in time is going to give you average jerk. So if there's jerking motion, if the acceleration is changing in time, you end up using the average acceleration formula. Okay, so free fall. Free fall is the motion under the influence of gravity and gravity only. It is the motion under the influence of gravity and gravity only. If gravity is the only force acting, it's known as free fall. That's what it means. So in free fall, do objects fall at a constant speed or do they accelerate? When you drop a ball, you know that the ball is going to go from 0 to something else. That's acceleration. When the ball is thrown up against gravity, it'll slow down to a stop, right? So that's also acceleration. So what do we know? We know that the following objects do accelerate. So when you drop an object, it's going to go from 0 to something else. And thrown up against gravity in the opposite direction of the gravitational pull, the objects will slow down to a stop. All right, so that's how you move. So the next question is, the following objects, do they accelerate at a constant rate? Or does the rate of acceleration vary? Does the rate of acceleration vary depending upon the weight? The answer to that question is the weight doesn't matter, right? Everything is going to follow the same. Everything is going to follow the same rate in the absence of air friction or when the air friction is negligible. Hammer and a feather drop from the same height. In the absence of air friction, then accelerate at the same rate. The rate at which the objects accelerate is going to be constant, so it's 9.8. We were using an approximation which is about 10. And Galileo is the guy who came up with this concept, roughly about 400 years ago. He said in a vacuum, in an airless environment, everything is going to accelerate at the same rate. All right, so the acceleration is constant, the motion is predictable, meaning that the free fall is predictable motion. So the g is the rate of acceleration, which is going to be constant. So if the acceleration is constant, you will know where the object is on the vertical direction, up and down direction. At any given point in time, you'll know exactly how fast the object is moving at that time. You'll also know how fast the object is moving at that location. That's what it means. All right, so 3 observations. You drop a ball, throw a ball in the downward direction, and you throw a ball in the upward direction. Drop a ball, throw the ball downward, throw the ball upward. All right, so 3 observations. And then we got 4 questions. Which ball has the largest acceleration? The one that you dropped or you throw in the downward direction, for example. All right, so you throw a ball in the downward direction, and you drop a ball in the downward direction. Which ball is the largest impact velocity? Which one is going to have the largest impact speed? The ball thrown in the upper direction or in the downward direction with initial identical speeds. So you throw a ball up, second ball down. You throw a ball up and down with identical speeds, and both balls at some point will reach the ground. So the question is, which one is going to have a larger impact speed? Throw a ball in the upward direction, and at some point it will come to a stop at the peak of its trajectory. So what's the acceleration of that ball at the moment it comes to a stop? What's the acceleration of the ball you're throwing it? While you're still in contact with the ball, while you're still touching the ball. All right, so you drop a ball. 1 second later, the ball is going to be here. 2 seconds later, it's going to be here. Gravity is going to take over. Gravity is going to induce a constant acceleration. So, which means that this ball is going to go from 0 to 10 within 1 single second. So that's what this number says. Acceleration is 10 meters per second squared, which means that it's going to gain speed in the direction of gravity at a rate of 10 meters per second each and every single second. So this ball is going to go from 0 to 10 within a single second, 10 to 20 within the next second, and that's it. That's the meaning of it. So what would happen if you were to throw a ball in the downward direction, say at an initial speed of 20 meters per second, all right? This ball is moving about 45 miles per hour. So once again, as soon as the ball leaves your hand, gravity takes over. So what will gravity do? It's going to make it go faster. It's going to make it go even faster. So it's going to take this speed from 20 meters per second in the next second up to 30 meters per second. And now this ball is going roughly about 70 miles per hour. All right, boom, it just went up. All right, so what happens to the next second? If you let it go, it's going to be moving at 40 miles per hour, 40 meters per second. Okay, so the acceleration here from within a single second, 0 to 10. So the acceleration is the same as gravity. And here the acceleration is 20 to 30. So within 1 single second, so it gained the speed of 10 meters per second within a single second. So it's, once again, the acceleration is 10. So once the gravity takes over, acceleration is constant. So it's going to be the same as the gravitational acceleration. So that's what it means. All right, so this next scenario that we will be looking at, that was our case number 1. Throw a ball up and down with identical speeds. Follow the ball going in the downward direction. As soon as the ball leaves your hand, next second it's going to be moving at 30 meters per second. Place the ground there. Throw the ball up. It's going up against gravity, so which means that going up against gravity has to slow down. So with the next second, it's going to be moving at 10 meters per second. Next second it's going to stop. Next second it's coming down. It's going to be at 10. Next second 20. And next second is going to be 30. Both balls will hit the ground at the same speed, not at the same time. So this is going to take 1, 2, 3, 4, 5 seconds. As this takes only 1 second. Okay, so the final speeds will be identical. All right, so final speeds will be identical. All right, so the next question. Notice that the ball, as soon as it reaches the trajectory of its motion, it stops, right? At that point. So at the moment that it stops, what's the acceleration? Most of you guys will say 0. Of course, your common sense is no substitute for education. Hopefully you guys are noticing it. It's not 0, is it? Speed is 0, not the acceleration. Acceleration is how fast the velocity changes in time. Is it moving before it stops? 1 second before it stops, it's moving. Fraction of a second before it stops, it's moving. A trillionth of a second before it stops, it's moving. A quadrillionth of a second before it stops, it's moving. If it's moving before it stops, and if it's moving after it stops, it's always accelerating. You can have one of the velocity 0. If the other one is not 0, it's accelerating. It's not a bus stop. It doesn't come to a stop there and stay there. All right, it's part of motion. It's some part of motion. It stops, but it's moving before and after, which means that it's always accelerating. All right, so what's that acceleration if that's the case? Well, you can just kind of assess that, right? Second before it's moving at 10. It goes from 10 to 0 within a single second, so which means acceleration is 10. But the next second it goes from 0 to 10, so which means that the acceleration is still 10. So it's accelerating. It's accelerating. The acceleration is always 10. So once the ball leaves your hand, the acceleration is always going to be the same as the gravitational acceleration. It's known as free fall. So free fall ends with impact. No question about it. Case that we focused on. This guy, a Canadian attorney, I don't know why, decided that he wanted to demonstrate the strength of the office windows in his office building. And what better way to do it other than just running to the window and throwing yourself at it? Guess what? It was wrong. The window, he shatters the window and then he plunges to his death. He fell 24 floors. All right, so we at least know, regardless of your nationality, you won't be able to survive a fall from that distance. So the question is, will the cats do better? All right, so I'm in Chicago, obviously. Chicago House is one of the tallest buildings in the United States, otherwise known as this used to be the Sears Tower. Today we call it the Willis Tower. It's about 1,450 feet tall all the way to the top. So what would happen if I were to go there and rip a cat and drop a cat from that height? Do you think that the cat is going to be able to survive that? All right, so the bird eye view perspective of what goes on. All right. First time I was preparing this presentation, this is like 20 plus years ago, we didn't have the option of having all these awesome sound effects that you could download from somewhere, so I had to use my own camera to generate the sound effects at my own detriment. I got scratched pretty badly because she didn't want to scream on her own. So a lot of you guys are thinking, oh, just like the Canadian attorney, this cat is not going to do too well. Splat is what you're looking at. The fact of the matter is the cats are set to have 9 lives, and there's a reason for it. Most cats will do just fine. In fact, the larger the distance of fall is, the better the cats will do, is a general rule. So the question is why? All right, so there are 2 reasons for it. The secondary reason is the one that we'll focus on. The primary reason is something that we'll focus on later on. So the reason why the cats tend to do better in longer distance falls, or shorter distance falls, regardless. Okay, so regardless, most cats will be fine, except they tend to do better in longer distance falls. They got extra muscles in their shoulders and hind legs. All right, so extra muscles, they're set to absorb impact so much better because using the muscles, the extra muscles, they can increase the impact time and reduce the acceleration. So that makes it easier to survive. And then we had our main observation, the person inside the elevator. And most of you guys came up with your own theories in the beginning of the semester. All right, so this is, once again, to demonstrate that your common sense is it's useless, guys. I'm very surprised that it didn't evolve into existence throughout time. And because people just form these opinions and it turns into these weird belief systems and all that stuff, and then people just rely too much on it. You got your own common sense as far as you guys were concerned, and this is to test the majority opinion. So you got this guy inside the elevator, cable snaps, elevator goes in a free fall, he's got a broken neck. All right, so he and his attorney are suing the elevator company for $100 million. So that's a recap of the story to recoup damages, right? All right, so if you're the animator, because you'll get it, as this all happens, and so they want you to do an animation to show what happened to him inside the following elevator. If they win, you get 10% of the earnings, that's $10 million. So that's the story behind it. Okay. As soon as I present that story to you guys, obviously a lot of you guys thought that you knew the answer. So this little storyboard, which is the final storyboard before the animation is done usually, is going to illustrate what you think happens inside a following elevator. All right, so he's happy, he's got a job, he's drooling, he's on the 13th floor, the cable snaps, stunned, goes up, hits the ceiling, what goes up, must come down, either the first or the second impact is going to break his neck. All right, so this is got to agree with you 100%. Most of you guys will go, okay, so that's what you're looking at is what you were visualizing in your head. All right, you figure that the guy went up, hit the ceiling, what goes up must come down, and then boom, he's got broken neck. That's it. Except when we did the demonstration, and what happens, the person doesn't leave the floor at all. All right, all of a sudden this says reality is completely different from what you were expecting. Elevator goes in a free fall. If the elevator goes in a free fall, the person is going to remain on the floor. There's no such thing as going up to the ceiling and then hitting the ceiling and coming back down. All right, so the question becomes why. So the person does not go up to the ceiling, and the question is why. The reason why the person does not go up to the ceiling is because of everything that we discussed so far. It's free fall. In free fall, everything falls at the same rate. In free fall, everything falls at the same rate. That's what it means. Yellow is the guy who came up with it. He said, hey, you know, blah, blah, blah. The guy, look, I'm a pizza guy. I get it. Look, everything falls at the same rate. This guy used to tell you, right? Everything falls at the same rate. But you're thinking about the elevator's heavier. Yeah, who cares? Well, it doesn't matter. Yeah, but there's air friction. Yeah, well, look, elevator is real heavy. Do you think that air friction is going to matter when something weighs a ton? No, it's a relatively short distance. This thing is super, super heavy. The amount of air friction acting on it is negligible. You're inside, you're shielded from the effects of air friction. So you're going to fall at the same rate as the elevator. That's it. You remain on the floor. You will remain on the floor. On top of that, there's a safety system. It keeps saying safety system. A safety system means it's there to bring the elevator to stop gently. Well, like if you've done the Six Flags, it's exactly the same as Six Flags. All right, they have a giant drop. You're in a falling elevator. You're in a free fall. You don't break your neck at the end of it, or else it doesn't work. People are not going to pay for it, right? It's exactly the same thing. This is exactly the same as a giant fall, giant drop, except this is the free version of it because you didn't pay for it. You happen to be involved in it. Or the Tower of Terror in Orlando. It's exactly the same problem. It's not supposed to break your neck. Yeah, we got a slight problem. The problem is you got a person with a broken neck right there. Oh, why did the person break his neck? This scenario even remotely possible? Yes, that question is yeah. I mean, it's highly unlikely that you'll ever find yourself in a falling elevator, but if you do, yes, you can break bones. It's just what happens.
Plunged
despite the safety
40
system.
stories. That story topped tonight's news briefs. Miraculously, the women suffered only minor injuries. One woman broke her ankle, the other broke her leg. After traveling down 6 floors, the elevator suddenly broke loose and began its free fall descent. Authorities are investigating the cause.
So you got 2 people inside. Elevator goes in a free fall. Safety system kicks in, and both people have broken legs. So you can break a leg, arm, back, neck. Absolutely, you can be paralyzed, or you can kill. All right, so what's average speed or velocity? Average speed is measured distance over measured time. Velocity is also what happens when you indicate the direction of that motion, right? So measured distance over measured time is going to be your average speed. When the direction is indicated, it turns into velocity. Average acceleration is how fast the measured velocity changes in time. So it's how fast the measured velocity changes in time. If the acceleration isn't changing in time, the motion is called jerk or jerking motion. You make motion predictable by fixing the acceleration at a constant rate. So which means that if you're speeding up at a constant rate, slowing down at a constant rate, or changing direction at a constant rate. If that's the case, the motion becomes predictable. What aspects of motion become predictable at constant acceleration? Well, 3 aspects will become predictable. All right, so the time is going to become predictable, obviously. If you know the time, you know the location, and you know how fast the object is moving at that time as well as at that location. So those are the 3 things that will become predictable. All right, so the following objects accelerate, they don't follow a constant speed. The experimental proof that the following objects accelerate is when an object is dropped, it's going to go from 0 to something else. Thrown up against gravity, it's going to slow down to a stop. The acceleration does not depend on the weight of an object. Everything is going to fall at the same rate. So the size doesn't matter, the weight doesn't matter. The value of acceleration during free fall is roughly about 9, it's roughly about 10. Actual number is 9.8. So that's going to be your next lab. All right, so I'm going to put up the lab this week. I'll give you guys 2 weeks to work on it. So there's a simple experiment that you will get to do at home to measure the acceleration due to gravity. Speed of an object 1 second after it's dropped, because the acceleration is roughly about 10 meters per second squared. It's going to go from 0 to 10 within the first second. Within the next second, it's going to be moving at 20 meters per second. So which object accelerates faster, the one which is dropped or thrown down with the larger initial speed, with a larger initial speed? All right, so the object which is dropped is going to go from 0 to 10 within a single second. If you throw the object in the downward direction, it's going to be moving 10 meters per second faster than the initial speed within the next second. Okay, so the accelerations will be the same. So both of them will speed up at the same rate. So by throwing it in the downward direction, in essence, you're providing it with an initial speed. That's what's happening. You throw it in the downward direction, you're providing it with an initial speed. What's the acceleration of an object thrown in the upward direction at the peak of its trajectory? At the peak of its trajectory, it comes to a complete stop, but it's moving before it stops and after it stops, which means that it's always accelerating. So which means that the acceleration will be the same as the gravitational acceleration. So it's going to be roughly about 10 because it's moving before, once again, let me repeat, because it's moving before and after it stops. Which object, the hammer or the feather, from the same height, reach the ground sooner on the moon's surface? The moon's surface, there's gravity, 1/6 of the gravitational pull of Earth. No air. In the absence of air friction, everything is still going to accelerate at the same rate. That's what it means. So which one is going to reach the ground sooner on the moon's surface? Neither. Both will reach at the same time. All right, so hammer or the feather, drop from the same height on the moon's surface. Which one is going to have a larger acceleration? The acceleration will be the same. All right, so that's as far as we got. But that's it. So there won't be any math problems or questions. All right, so test number 1 and test number 2 operates are available. So if you got less than 7, take care of the test. So the operate tests are available, obviously, until Sunday midnight. If you got less than 7, you have to get 7 or better in order to get a 7. All right, so 7 is a passing grade. That's what you need in the worst case scenario, obviously. All right, so I'm allowing 2 attempts instead of 30 minutes. You got 20 minutes. It's an upgrade test. 2 attempts at the upgrade test. So I'm going to keep the better grade, obviously. And then if it's 7 or better, I'll give you an upgrade of 7 on your original test. That's what it means. Test number 3 on the stuff that we just covered, uniform motion, is going to be available tomorrow at midnight in the morning, obviously, until once again Sunday midnight. And it's going to be over the stuff that we just finished up. So that's pretty much it. So